Ever wondered why time seems to fly when you're having fun but drags when you're bored? Could it be that time changes based on our perception, or is there more to it? Welcome to the enigma of space-time, a concept that challenges our everyday experience of time. When we think of time, we often imagine it as a constant flow, unchanging and impartial. But what if I told you that's not entirely accurate? Enter the world of Einstein and his theory of relativity. Einstein proposed that our understanding of time is flawed because it fails to account for the interconnectedness of space and time. He suggested that space and time are not separate entities but interwoven into a four-dimensional fabric known as spacetime. This fabric is not static. It bends, stretches, and warps in response to the objects within it. Imagine a trampoline. When you place a heavy ball in the middle, the surface warps under its weight. Similarly, space-time warps around massive objects like planets and stars. And just like a ball rolling towards the heavier object on the trampoline, smaller objects move towards the heavier ones in space, creating what we perceive as gravity. But the real mind-bender here is that this warping of space also affects time. The closer you are to a massive object, the slower time moves. This is a phenomenon known as time dilation. It's why if you were to stand on a neutron star, one of the densest objects in the universe, your watch would tick slower than a watch back here on Earth. So, our perception of time as constant is merely an illusion. In reality, time is a dynamic entity influenced by the curvature of space-time around us. It's a concept that's as fascinating as it is complex, one that continues to baffle even the brightest minds. So it turns out, time isn't as straightforward as it seems. It bends, stretches, and warps around the universe. Hard to believe? Let's dive deeper. Imagine you're aboard a spaceship traveling close to the speed of light. Would time pass at the same rate for you as it does for someone on Earth? This, my friends, is the crux of one of the most mind-bending concepts in physics, time dilation. Let's unravel this conundrum together. Picture yourself on a spaceship, cruising at a velocity that's close to the speed of light. Back on Earth, your best friend observes your journey. To them, each second on your spaceship appears to tick by slower than each second on Earth. This isn't some cosmic illusion or a trick of the light. It's the reality of our universe as dictated by Einstein's special theory of relativity. Now, you might wonder, why does this happen? It all boils down to the fundamental laws of physics, which state that the speed of light is constant. It doesn't matter if you're standing still or hurtling through space at breakneck speeds, light will always zip by you at the same rate. Here's where things get a bit tricky. If you're moving at a speed close to light, and light itself always has to move at its constant speed, then time has to make up the difference. It does so by stretching itself out, by dilating. The faster you move, the more time dilates, and the slower it appears to pass for you compared to someone stationary. But that's not all. Time dilation isn't just affected by speed, it's also influenced by gravity. This is a consequence of Einstein's general theory of relativity, which tells us that massive objects warp the fabric of space-time around them. The stronger the gravitational field, the slower time passes. So if you're on a planet with a stronger gravity than Earth, your clock will tick slower than an Earth clock. So, not only does time differ based on where you are in the universe, but it also changes based on how fast you're moving. Intriguing, isn't it? From the heart of black holes to the farthest reaches of the cosmos, the dance of space-time continues, forever shaping our understanding of the universe. Now, what if we told you that massive objects like the Sun and Earth aren't just sitting in space, but they're actually bending and curving it? Yes, you heard that right. Space is not a fixed, unchanging stage where the cosmic dance unfolds. Instead, it's more like a flexible fabric that can stretch and curve. This idea is an integral part of Einstein's theory of general relativity. So how does this bending and curving happen? It's all about mass and gravity. You see, according to Einstein, massive objects cause the fabric of space-time to curve. In practical terms, think of space-time as a massive rubber sheet. Now, if you place a heavy bowling ball on this sheet, it will create a dent, a curve. This is exactly what happens in our universe. Massive objects like the sun, the earth, or even a black hole cause a similar curvature in space-time. Now you may be wondering, what does this have to do with gravity? Well, everything. This curvature in space-time is precisely what we perceive as gravity. Imagine rolling a marble on our metaphorical rubber sheet with the bowling ball. The marble will naturally move towards the bowling ball, not because of an invisible force pulling it, but because of the curve created by the bowling ball. The same happens with the Earth and the Sun. The Earth is not just being pulled towards the Sun, it's following the curve that the Sun creates in space-time. This concept fundamentally changed our understanding of gravity. Before Einstein, gravity was seen as a force between two objects. But with the theory of general relativity, we now understand that gravity is not a force per se. It's the curvature of space-time caused by massive objects. So gravity is not just a force pulling objects together, but a curvature in the fabric of space-time. Quite a twist, right? And this twist is what keeps our universe in a beautiful perpetual dance. It's the cosmic ballet choreographed by the curvature of space-time. So we've unraveled some mind-boggling concepts today. But what does it all mean for us in our daily lives? It's quite a journey we've been on, isn't it? We've delved into the enigma of space-time, plunged headfirst into the depths of space-time relativity, and navigated the curvature of space-time. Here's the takeaway. Space and time are not separate entities, but rather intertwined in a cosmic dance that shapes our universe. This understanding changes our perspective. We're not just inhabitants of a static universe, but active participants in a dynamic, ever-changing reality. Our comprehension of space and time relativity also emphasizes our place in the cosmos. We are not insignificant specks, but integral parts of a vast and intricate tapestry woven by the threads of space and time. While these concepts might seem far removed from our daily lives, they're integral to understanding our universe. And who knows, maybe one day we'll harness the power of space-time relativity. Until then, keep wondering, keep exploring,